In this video, I'm going to show that there are different sizes of infinity using Cantor's diagonal argument. But first, I would like to explain what we mean by different sizes for infinity. Let's first examine the finite case. Imagine you have two jars full of marbles, and you would like to know if they contain the same number of marbles. You might try to count how many there are in one jar, then in the other, and if you get the same result, there are as many marbles in one jar as in the other. Seems simple, right? But that's actually a bad way to go about it. It's bad because, well, you have to count, then you have to memorize, then you have to count again, and it's not easy to see how we would do this for infinity. Let me try another way. I'm going to take one marble in each jar. I pair them up, setting them side by side, and then I just forget about them. Then I do that again and again. Now, if at one point one of the jars becomes empty while the other still has marbles, then they don't contain as many marbles. And on the other hand, if I can pair up all the marbles in one jar with all the marbles in the other, they contain just as many marbles. With this method, there is no counting and no memorizing. Even better, it's very easy to generalize this process to infinity. All I need is to find a rule that pairs up all the elements in one set with all the elements in another set in a one-to-one relationship. No one left out, no one paired to multiple others. If I can find such a rule, I will say my two sets have the same number of elements, whether finite or infinite. Let's take an example. The whole numbers and the even whole numbers. You would think there are twice as many whole numbers as there are even whole numbers, right? Since in the second set we just took half of them out. But no, there are exactly as many. Here is the rule. Each whole number will be paired to the even whole number that is twice as much as him. It's a simple rule, but you can see that no one is left behind, and they are all only paired to a single other number. And so, since I have found a suitable rule, this means there are exactly as many whole numbers as there are even whole numbers, not twice as many. You may say, well, if I have two infinities at my disposal, I can always find a rule to pair them up. But Cantor's diagonal argument shows otherwise. It goes like this. I'm going to make a list of all the real numbers being the numbers with decimals. This will show that there are as many real numbers as there are whole numbers, because that is the same as pairing the first real number with the whole number 1, pairing the second real number on my list with the whole number 2, etc., etc. And so writing this list will be the same as finding a rule that pairs each real number to a whole number in a one-to-one relation. But such a list cannot exist, and here's why. Let's assume we did find such a list. No matter what it is, I can always find a new number that won't be on this list. Here's how I can make one. I just make sure that this new number is always different than all the other ones on the list. If the first digit of the first number on the list is a 1, then the first digit of my number will be anything else. Let's say 2. And if it's anything else, then the first digit of my number will be a 1. So these two numbers will differ on the first digit. And so my number cannot be the first number on the list. I do the same for the second number on the list with the second digit, and so on, and so on. And so in the end, my number can't be anywhere on the list. And so the list does not contain all the real numbers, and so this list could not exist in the first place. This means I can't pair up the whole numbers and the real numbers. So these two sets can't be of the same size, even though they are both infinitely big. And since the whole numbers are a part of the real numbers, this means that the real numbers are a way bigger infinity than the whole numbers.